Okay, in this next section, we're discussing in 2.1 the tangent and velocity problems. Before we do that, we just need to talk a little bit about limits and derivatives, since that's what Chapter 2 is discussing. Okay, it's appropriate to begin our study of calculus by investigating limits and their properties. Now, the special type of limit that is used to find tangents and velocities gives rise to the central idea in differential calculus, which is the derivative. Now, we're going to see how derivatives can be interpreted as rates of change in various situations and learn how the derivative of a function gives information about the original function. So in this section, we see how limits arise when we attempt to find the tangent to a curve or the velocity of an object. Now, the tangent problem. Now, the word tangent is derived from the Latin word tangens, which means touching. Thus, a tangent to a curve is a line that touches the curve. So, in other words, a tangent line should have the same direction as the curve at the point of contact. How can this idea be made precise? Now, for a circle, we could follow the geometry rules followed by Euclid and say that a tangent is a line that intersects the circle once and only once, as you can see in figure A, which is the first one. Now, for a more complicated curves, this definition is inadequate. So if you take a look at that second curve, it shows that two lines, L and T, are passing through a point P on a curve C. The line L, intersects the function C only once, but it does not look like we can think of it as a tangent. Now, line T, on the other hand, looks like a tangent, but it intersects C twice. So to be specific, let's look at the problem of trying to find a tangent line T to the parabola y equals x squared in the following example. Okay, so for example number 1, we want to be able to find an equation of the tangent line to the parabola y equals x squared at the point 1, 1. Okay, so we will be able to find an equation of the tangent line t as soon as we know its slope m. Now, the difficulty is that we know only one point P, which is on t, whereas you need 2 points to be able to compute the slope. Now, but observe that we can compute an approximation to m by choosing a nearby point. So if you look here at the graph, we have point 1, 1, and then on that curve, we're picking another point called x and then x squared. Since that is our graph, y equals x squared, well, we know arbitrarily the first point would be considered x, and the y coordinate would then be x squared. So now we can just pick an arbitrarily point called x and x squared. So now what we want to do, is to be able to compute the slope of this line PQ. Now the slope of the line PQ right now, is called a secant line. So this blue line, and let me go ahead and represent that in a color blue. So the blue represents a secant line. And that's from the Latin word secans, which means cutting. And what it does is that the line that cuts or intersects a curve more than once. So a secant is different than a tangent, because a tangent touches it at one point, whereas the secant is touching it at more than one point. So what we want to do is we want to be able to determine, what is the slope of the line PQ. So let's find the slope of the line PQ. Okay, now we're going to abbreviate it that way. And so remember that it's the change in y over the change in x. And since you're using the points 1, 1 and x squared 1, well, we can say that x squared represents y2 and y1 is minus 1. Okay, and then x2 is x, and then we can subtract 1. So again, we have an arbitrary formula for a slope, okay, where x can be any real number. So let's just go ahead and pick points, right? So for example, we're going to pick the point for Q, okay, to be an x coordinate of 1.5. and a y coordinate of 2.25. So let's plug it into our slope. Okay, I'm going to start over here, and I'm going to show you why. Okay, so if you have the function y equals x squared, all right, and let's say that we're going to put in 1.5 since that's the number that comes after 1. So y would then equal 1.5 squared. And 1.5 squared is equal to 2.25. So what that does is that's going to give us an input of 1.5 where the output is 2.25. Okay, so let's use that particular point to determine what would the slope be for 1.5, 2.25, and 1, and then 1. So using the formula, the slope of MPQ, well, what do we get for x squared? Well, we got 2.25. And then we're going to subtract 1 since that is the point that's on the line. And then we're going to take 1.5 and then subtract 1. Okay, so what number do we get here? Well, we get the value of 2.5. So that gives us that slope. Okay. Now, let's go ahead and then pick another one. We're not going to do every single one, but at least want to show you what's happening. So again, using y is equal to x squared. Okay. All right, now, so we know here that this point is 1, 1. So from here, it's from 0 to 1, okay? And then it increases on the x-axis. Now, if you look at the tables in the margin, okay, that's shown here, the values of the slope for several values of x close to 1. So we want to find values that are closer to 1, that are getting closer to 1. So we started with 1.5, right? Okay, and technically we start at 2, and we get a slope of 3. Okay, we get a start at 1.5, we get a slope of 2.5, which is what we just did here. Now let's go ahead and plug in 1.1. So if we plug in 1.1 for x, so we get 1.1 and square that. Okay, and then what happens when we take 1.1 and then we square that? Well, if we take 1.1 and then square it, then that should give us 1.21. Okay, so again, using the same procedure from our previous step, we know that the input is 1.1, the output is 1.21. And so now what we want to do is we want to find the slope of the line 1, 1 close to 1.1 and 1.21. So let's go ahead and discover that. So we have MPQ, okay, and we know that Y2 is 1.21, and we're subtracting 1. and then we're going to take 1.1 and then subtract 1. Okay, so what happens there? Well, you have 1.21 minus 1, and you're dividing that by 1.1 minus 1. And so now you end up getting a slope of 2.1. Okay, so you can see here that that's how we're determining the slope. So when we plugged in 2 for x, okay, we get an output, okay, and then that gives us that allows us to be able to see the slope when it's at 3. Okay, and then 1.5 decreased to 2.5. And then at 1.1, the slope decreased to 2.1. And then at 1.01, it then decreases to 2.01. And at 1.001, it decreased to 2.001. So you can see here that as you look and pick a value for x, okay, it's closer and closer getting to 1, but the slope is getting closer and closer to what number? 2. Because it's going from 2.3, 2.5, 2.1, 2.01, and 2.001. Okay, now if we do the same thing on the other side of 1, so again, we're looking at the values of 1, and we're figuring out, okay, what happens as you get closer to 1 on this side, and what happens when you get closer to 1 on this side? What's happening with the slopes? Now over here, okay, if we pick 0 as our first point, and we plug it in to our function, we also get 0. So if we want to find the slope of that, we get 1. Okay, following the same procedures of what we did for 2 and 3. We increase 0 to 0.5, plug it into the slope formula, and we end up getting 1.5 as a slope. And then 0.9 goes to 1.9. 0.99 goes to 1.99. And again, what it's showing here is that the slope going from 0 to 0.99 is approaching 1.99, which is 2. And then on the other side of this, okay, as 2 then is getting closer and closer to 1, then again, it's also getting closer and closer to 2. Okay, now, the closer q is to p, then the closer x is to 1, and it appears from the tables that the closer MPQ is to 2, this suggests that the slope of the tangent line t should be m is equal to 2. Now, we say that the slope of the tangent line is the limit of slopes of the secant lines, and we express this symbolically by writing the following. We would say that the limit, okay, as q approaches p of that slope MPQ is equal to the slope of that line. And we know that the limit as x approaches 1 from the left and the right side of x squared minus 1 over x minus 1 is equal to 2. Okay, now assuming that the slope of the tangent line is indeed 2, then we use the point slope form of the equation of a line to write the equation of the tangent line. So now what we can do is, in order to find the equation of the tangent line, well, what do we know? We're assuming that the slope would then equal 2, and what was given in the problem was a point at 1 and then 1. So now we can use the point slope form to find our equation. So let's go ahead and do that. We have y minus y1, which is equal to m times x minus x1. So we have y minus 1, which is equal to 2 times x minus 1. Y minus 1, which is equal to 2x minus 2. and therefore y was equal to 2x minus 1. Okay, so this is the equation of the tangent line through the point 1, 1. Okay, so I'm going to go ahead and bring this figure down here as well. Okay, so what it's saying here is that this line that represents the blue line here, okay, touches, okay, that function, the parabola, and therefore that is going to represent the equation y equal to 2x minus 1 as your slope. Okay, now if we take a look at this figure here, it's going to illustrate the limiting process that occurs in this example. So as Q approaches P along the parabola, the corresponding secant lines rotate about P and approach the tangent line T. So let's take a look at an animation that describes this situation. So here, again, using our animation, okay, we have a tangent line to a curve at a point P, which is defined to be the line through P. So it also has a slope, which is the limit of slopes of secant lines PQ as Q approaches P along the curve, and therefore as H approaches 0. Okay, now let's take a look at this. Okay, we're going to select one of the three available functions, which is what we did. We have x squared, since that's what was our example. Okay, and then we're going to drag the A slider, okay, which is this one. This is the A slider, okay, or click on a number above slider to select the point on the curve at x equals A. Now, likewise, okay, we're also going to select the slider to choose an initial value for H. Okay, and you can then change the value of H with the slider and observe the effect on the secant line shown on the graph. Okay, so indicated by the blue lines. So the blue line passing through the red and blue dots when the secant checkbox is selected. And note that the secant slope is not defined when H is equal to 0. Okay, so let's see what happens when it gets to 0. Okay. You can turn the tangent and secant lines on or off by clicking the appropriate checkboxes up at the left. So what it's saying here is if you turn this off, the secant is off. If you turn a tangent off, there's no tangent. Okay, but let's go ahead and click the tangent line. There's your tangent line. Okay, and so what's happening with the tangent line, you can see here that as you move along this curve, okay, you have different slopes of that particular line. Okay, likewise, okay, let's see what happens if you put a secant triangle next to it. Okay, well, sorry, it has to be on the secant option. So if we find the secant line, okay, what does this secant line do? Well, again, it passes through at more than one point. Okay, if we put a secant triangle in, that also tells us that it's a 90-degree triangle, but we'll see that later on in this class. Okay, now over here, if you notice that you have the slopes, right? And then you have the rate of change, which is the difference quotient. So again, this kind of gives you a good idea to be able to see what's happening here. So here is your series of slopes. Okay, so let's go ahead and move A a little closer here. Okay, so here's your secant line. So there's your slope. And then if it changes on the other side, then the slope changes there. Okay, so again, that's because that represents the right triangle. Now going back to these corresponding secant lines, okay, here you have the different variations of Q. All right, so Q is approaching P from the right, and whereas Q is approaching P from the left. So many functions that occur in science are not described by explicit equations. Okay, they are defined by experimental data. And then the next example shows how to estimate the slope of the tangent line to the graph of such a function. Okay, so example 2, we're estimating the slope of a tangent line from experimental data. The flash unit on a camera operates by storing charge on a capacitor and releasing it suddenly when flash is set off. Now, the data in a table describe the charge Q remaining on the capacitor measured in microcoulombs at time t. We want to use the data to draw the graph of this function and estimate the slope of the tangent line at the point where t is equal to 0.04. So we're looking at this point. So when t is equal to 0.4. Okay. Now we want to make note that the slope of the tangent line represents the electrical current flowing from the capacity to the flash bulb. Okay, so here we have our table of points. Okay, and then in this figure, what we do is we plot, okay, the points given the data and then use them to sketch a curve that approximates the graph of the function. So here is the curve that approximates the graph of the function. Now, if we look at the given point, which is 0.04 and 67.03, okay, let's go ahead and do that. So if we look at the given point, which is 0.04, 67.03, okay, and that represents a point P that would be on this graph, okay, and we have an initial point that starts at 0, and we'll call that R. So at 0.00, what is the output on the table? Well, it's 100.00. Okay, so now we want to be able to find the slope of PR. Okay, so again, let's take a look at this. So we have 0.04, okay, with an output of 67.03, right? And then at 0, 0, we have 100. And so what we're doing is that we're trying to find the slope of this line right now. Okay. So let's find a slope. So we take 100, subtract 67.3, and then take 0.00, subtract 0.04, and that will give us approximately negative 824.25. Now, looking at the table here, okay, here is the ordered pair 0, 0, 100.00, okay, and then we got the slope of that to be negative 824.25. Similarly, if we go to use 0.02 with an output of 81.81, then we get the slope of negative 742. And then you can see here that it's actually increasing. So the slope is actually increasing from negative 824 all the way to 504. Okay, so now if we want to, this table, we want to be able to expect the slope of a tangent line at t is equal to 0.04 to lie somewhere between negative 742 and negative 607.50. Okay, so if we wanted to figure out, okay, what is the slope that's in between here? Okay, well, we can find the midpoint of that. In order to find the midpoint of that, we can take half of that average. So we're going to take negative 742.00 minus 607.50. Okay, so if we combine those two and then divide it by 2, then we should get something sort of in between. And what we get in between those slopes is negative 674.75. Okay, so by this method, we estimated a slope of the tangent line to be negative 675. So if we estimated that, it would be negative 675, which is in between those two slopes. Now, another method is to draw an approximation of the tangent line at P and measure the sides of the triangle ABC, okay, as in figure 4. Okay, and that figure is right up here. All right, so we want to find, okay, so we're looking at AB, right? And then this represents BC. So this is the change in Y over the change in X. So the change in Y is actually the distance, negative AB, and the change in X is BC, so therefore it's BC. Okay, so that represents the slope, right? But we know it's going to be negative because it's going down. So what we want to do is we have negative, we want to find the absolute value of the distance from A to B divided by the absolute value of the distance from B to C. Okay, so if we take a look at the distance between A and B, okay, well, we know it's going to be a negative, and the absolute value of that distance is taking 80.4 and subtracting 53.6, dividing that by 0.06 minus 0.02, which then gives us a result of negative 670. Now, the actual physical meaning of what we just solved for is that the electric current flowing from the capacitor to the fresh bulb after 0.04 seconds is about negative 670 microamperes. Okay, now what we have is called the velocity problem. Okay, now if you watch the speedometer of a car as you travel in city traffic, you see that the needle doesn't stay still for a very long time. And that is, the velocity of the car is not constant. So we assume from watching the speedometer that the car has a definite velocity at each moment. But how is the instantaneous velocity defined? Let's investigate the example of a falling ball. So the velocity of a falling ball, so suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, which is 450 meters above ground. Now we want to be able to find the velocity of the ball after 5 seconds. Now, though experiments carried out for centuries ago, Galileo discovered that the distance falling by any free falling object is proportional to the square of the time it has been falling. Now, this model for free falling neglects air resistance. So if the distance falling after t seconds is denoted by s of t and measured in meters, then Galileo's law is expressed by the equation. So Galileo's law is expressed by the equation, which we need to know, okay, is s of t, which is equal to 4.9 t squared. Okay, now the difficulty in finding the velocity after 5 seconds, okay, according to the question, is that we are dealing with a single instance of a time equal to t equal to 5. So no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief interval of a tenth of a second. So we can go from 10, then 5, and then to 5.1, and then 5.05, 5.01, because again, you're looking at the difference in terms of a tenth. Okay, so in order to find the average velocity, okay, that's equal to the change in position all over the time elapsed. Okay, so let's go ahead and put the formula to test here. So that means since we're starting with, if we want to look at t equals 5 to t is equal to 5.1, well, let's look at that average velocity here. So the change in position would then be s of 5.1 minus s of 5 divided by, in this case, the time elapsed, and the time elapsed was 0.1 because it'd go from 5 to 0.1. Okay, and so what we're going to do now is substitute these values into the function that's given up here. So we're going to get s of 5.1, which means you're taking the function 4.9, multiplying it by the value of 5.1, and then squaring it, minus 4.9 times 5 squared all over 0.1. And so now when you do the division, you get approximately 49.49 meters per second. Okay, so if you notice, that's this interval here. Okay, we have between 5 and 5.1, we got an average velocity of 49.49. Okay, and then if we wanted to, okay, we could then try the next interval. Okay, and then just to save time here, okay, we know that we have, I'll use different color here. If we want to look at this time interval here, so we know that t is equal to 5, and t now is equal to 5.05. So again, we want to find s of 5.05 minus s of 5 divided by, in this case, now it's going to what? 0.05. And so we got 4.9 times 5.05 squared minus 4.9 times 5 squared all over 0.05. And then again, this becomes approximately 49.245. Okay, now, as you can see in the table, it appears that as we shorten the time period, okay, the average velocity becomes closer to 49 meters per second. So that means that as we change this interval here, right, it gets closer and closer to 49, okay, meters per second. And so we would say that the instantaneous velocity when t is equal to 5 is defined by the limiting value of these average velocities over shorter and shorter periods of time that start at t is equal to 5. Thus, the instantaneous velocity after 5 is 49 meters per second. So at t is equal to 5, again, we can say that the instantaneous velocity is equal to 49 meters per second. Okay, last, you may have the feeling that the calculations used in solving this problem are very similar to those used earlier in this section to find tangents. But in fact, there is a close connection between a tangent problem and the problem of finding velocities. If we draw the graph of the distance function of the ball, as you can see here in figure 5, okay, and then we consider the points A 4.9a squared and q is a plus h 4.9 times a plus h squared on the graph, then we would get the following slope of the secant line. So again, you're using that rate of change formula. In this case here, this is the same as the average velocity over the time interval a and a plus h. Therefore, the velocity at time t is equal to a, and therefore the limit of these average velocities as h approaches 0, it says must be equal to the slope of the tangent line at p. So the limit of the slopes of the secant lines.